So if we have a vector, say A, we'll call it, and A has components A1, A2, and A3. The length of the vector, and the way we conceptualize this, is it will be the length of the line from the origin to this position vector. And how do we calculate that? Well, if you want to go through the exercise yourself, we can derive a formula using Pythagoras' theorem. So say this is the point A. Okay, if we drop that down to this line here, there's a right angle triangle down into where it is in the middle. There's a right angle triangle there. Okay, and so on. And you can mess around with these right angle triangles, and you eventually get the formula. And this works in all dimensions, not just in 3 dimensions. That might, of course, in 4 dimensions, the geometric interpretation doesn't quite add up, but it's just a definition. So this would be A1 squared plus A2 squared plus A3 squared. So that's how you calculate that. That leads us on to finding the distance between 2 points. So say we have another point B, and B has components B1, B2, B3, and we want to find the distance between the position vector B and the position vector A. Well, what do we have to do? We have to find a vector between A and B. So that vector would be B minus A, as we looked at in the last video. So the vector between A and B is given as such, A3, sorry. And then if we want to find the length of that vector using the same formula, it's just now instead of A1 we've got B1 minus A1 all squared plus B2 minus A2 all squared plus B3 minus A3 all squared. So that is our formula for finding the distance between 2 points A and B, and of course whatever vectors you're given you can just substitute in different values accordingly. We'll now go on to look at the Ruvat equations. For constant acceleration in 1 dimension we had something called the Suvat equations, and here we call them the Ruvat equations, and again these only apply for constant acceleration, but this time acceleration is a vector, so we've got some acceleration in the x-axis, some acceleration in the y direction, and some in the z direction. Okay, so overall that obviously leads to one acceleration in one particular direction, but we can break it up into this component-wise manner, which makes it easier to digest and work with. So again, this is for constant vectors, so A can't be a function of time, otherwise these formulas don't work. And they're called Ruvat because instead of having distance or displacement S, we talk about the position vector R, and then we introduce R0, which is some initial position. So essentially these equations are the same as the Suvat equations, but S is replaced with R minus I R0. Okay, so that's like displacement, it's final position minus initial position, but it's often easier to just include R0 in the formulae for these equations. So let's have a look at the equations we get. A lot of them should be familiar. So V is equal to A multiplied by T plus V0. So here V0 is like our U in 1 dimension, and T you can see it's not underlined, whereas all the other things are. So T is a scalar quantity. Time is obviously not a vector. Okay, and this equation is exactly the same as the 1-dimensional form. A couple of things to remember when looking at these equations. When I underline, this is my notation anyway, and a common notation is also, if it's been made on a computer, is to have it in bold, but you obviously can't draw bold, so if you're doing your working out, try to underline things. And if your equation has something weird, like these two terms involve underlinings and this last one doesn't, something's gone wrong. Okay, you can multiply a vector by a scalar, but you can't add a scalar to a vector, so that wouldn't make any sense. So make sure you're double checking any equations you get. The next one is R is equal to R0 plus V0 T plus 1/2 AT squared, and again this is exactly the same to the equation we have in 1 dimension, which is S is equal to UT plus 1/2 AT squared, but of course we've added in this R0 term and brought it over to this side as well, because we're assuming we'll be interested in the final position. And yeah, u we've replaced with v0 just because in this vector notation, if we're talking about an initial position r0, or u would be the speed at r0, so it kind of makes more sense to call it v0, just so that it's all lined up, the notation. Yeah, so r sort of corresponds to v and r0 corresponds to v0. Another equation that's almost a direct analog is this one here, v plus v0 t. Okay, so again we have this equation almost exactly. S is equal to a half v plus ut. So that's nice and simple. And then we actually have an extra equation. We don't deal with, well, I'm not going to list it here, with the one that involves squares, because that's a little bit difficult to generalize into vector form anyway. Because we haven't even talked about the ideas of vector multiplication yet. You can do it, but it won't be required at this level. So we're going to introduce a new equation, which is r is equal to r0 plus the final velocity times t minus 1/2 at squared. And this might be, you're given the final velocity and you want to find r, and you've got acceleration and time and the initial position, and instead of calculating the initial velocity and then plugging it into this second formula here, you can just have this formula, which works quite nicely. You can also do this in the one-dimensional case. It's just in one dimension. It's not really a big deal to make these calculations and such, so there's no point in deriving a whole new formula. Here, how would you get this formula? Well, you just take this one here and you write that v0 is equal to v minus at, and you just plug that in, collect some terms, and you get this formula here. Okay, so that's it for this video, and that wraps up the whole A-level series we're doing here on the channel. Thank you very much for watching and supporting the channel. Please like the video if you did learn something useful, and I hope to see you in the next